Okay, so we are going to start looking at differences between two proportions or two populations just to compare for any difference between the means from two populations or the proportions from the two populations. So we're looking at differences. And just to remind you, differences have ways that have behavior that we kind of understand. This goes back to lesson or section 5.2, and my screen is frozen, so one moment. Okay, so lesson 5.2, where we looked at one population, we call it X, another population, we called it Y, and what we did at one point was we looked at every X minus every Y. I think that's what this one is. What does the distribution of X minus Y look like? And the idea was that as long as the X's were sort of bell-shaped and the Y's were bell-shaped, when you take every X and you subtract every Y, that comes out bell-shaped too. Also, the mean of the differences is the difference of the means. So there's a rule down here that says that the expected value of a difference, I'll wiggle it, this one right here, the expected value of a difference is the mean of differences. It's the difference of the expected values, which are the means. And also the variances are interesting because even though you're subtracting the variables, the variances add, okay? And that differences also have bell shapes as long as the populations you're starting with are bell shaped. So I think we can kind of summarize that. So we're going into chapter 9 now. I hope you were able to print the notes if you're writing on paper. Let me just go ahead and remind you of the basic rules that we were just looking at, that the expected value of X minus Y is expected value of X minus the expected value of Y. So the mean of differences is the difference of the means. The variances are weird. The variance of a difference is the sum of two variances. And then the last statement is if X and Y are normal or approximately normal, then the difference is normal. X minus Y is normal. Okay. All right, so let's just go ahead and read this. It's a lot of language. So here it says, here we lay foundations for a hypothesis test that can compare two population parameters, either means or proportions. We start with the proportions here. When we estimate a population proportion P, we use a sample proportion P hat. The mean of all sample proportions is mu sub P hat, and it turns out that the mean of sample proportions is P, the population proportion, and the standard error or standard deviation is sigma P hat, which is the square root of PQ over M. That's the standard deviation of p hats, and if you square that, you get the variance of p hat values, which just squaring makes the square root go away. So it's just PQ over M. And sample proportions are approximately normal if NP is at least 10 and NQ is at least 10. So all of that's sort of old info. If we want to compare two population proportions, P1 and P2, using sample proportions P hat 1 and P hat 2, from independent samples, we subtract the population proportion. Just to see, remember the mean difference is the difference of the means. And I think, yeah, we subtract them. The difference between the population proportions is estimated using a difference between sample proportions, P hat 1 minus P hat 2. When we want to determine if such a difference is significant, we compute the z-score, but this requires a mean and a standard error. So the mean difference is the difference between the means. So remember what the formula we had just up above. The mean of a difference, p hat 1 minus p hat 2, is the expected value of the difference, p hat 1 minus p hat 2. But that's the difference of the expected values, the expected value of p hat 1 minus the expected value of p hat 2. And the expected value is the mean. And remember up here, right here, the expected value of p hat is p. Okay, remember the mean is the expected value. So the expected value for the first sample proportion is the first population proportion, minus the expected value for the second sample proportion, which will be the second population proportion. So that's going to be the mean for a new z-score. The variance of differences is the sum of the variances. So the variance of a difference between p hat 1 and p hat 2 is the variance of p hat 1 plus the variance of p hat 2. And then you just have to remind yourself what a variance of a sample proportion is. Here's the standard deviation of a sample proportion. It's just the square root of PQ over N. And so the variance squares it, and you just get PQ over N. But there's two of them. So you have a variance for the first population, which would be P1, Q1 over N1. And it's the sum of the variances. So then you have to do a P2, Q2 over N2. Okay, and then the standard deviation is the square root of the variance. So you just take the square root of that for the standard deviation. These have different denominators, so they can't be combined. Just leave it like that. Okay, so that's the standard error. And so then if you want to take a z-score between two sample, a z-score of a difference between two sample proportions, here's the difference, p hat 1 minus p hat 2, and then you would subtract the mean difference and divide by the standard error or the standard deviation of the differences. So this would be p hat 1 minus p hat 2. Okay, that's the difference. And then you subtract the mean difference, which we said up above here is P1 minus P2. We put in parentheses. Okay, over the standard deviation of differences, which somehow I don't want to write again, so I'm just going to copy and paste this. There we go. So that's our next z-score. It's going to be tweaked a little bit. We'll talk about that when we use it. I think we'll wait. Okay, so that's the difference between two proportions. The only other thing we study in statistics, besides proportions, are means. So that I can handle a difference of two proportions, but what about the difference of two means? So let's go ahead and read this next part. We're going to do the same thing now with means. When we estimate a population mean, we use the sample mean, x bar. Population mean is mu, sample mean is x bar. The mean of all sample means is mu sub x bar equals mu, that's the population mean. And the standard error is sigma sub x bar, which is sigma over the square root of n. And what we're mostly interested in is the variance, which is the square of the standard deviation. So you get sigma squared over n, and you square that. Sample means are approximately normal if the sample size is bigger than 30, or if the population we're sampling from is normal. If we want to compare two population means, mu1 and mu2, using sample means, x bar 1 and x bar 2, from independent samples, we subtract those two sample means. The difference between the population means is estimated using the difference between the sample means. When we want to determine if such a difference is significant, we compute the z-score, but this requires a mean and a standard error. And again, remember, mu is a population mean, and the variance in a sample mean is sigma squared over n. So the mean of all differences we need first. So that's the expected value of differences. And expected value of differences is the difference of two expected values. Okay, but the mean of a sample mean is the population mean. So the expected value of x bar 1 is mu1. And the expected value of x bar 2 is mu2. So this is the mean that we'll use in our z-score. That will eventually turn into a t-score because you're not going to know the population standard deviations. We also need the standard deviation to compute a z-score. We start with the variance. The variance of differences is the sum of the variances. So this is going to be the variance of x bar 1 plus the variance of x bar 2, like that. Okay. Now, variance of a sample mean, as you may remember, is right here. Variance of a sample mean is the population standard deviation squared over n. That's sigma squared over n. Okay, so, but there's two of them. So you'll have a sigma 1 squared over n1 plus a sigma 2 squared over n2. The variance of the differences is the sum of the variances. And then standard error is the square root of variance. So we'll just take the square root of that thing up there, sigma 1 squared over n1 plus sigma 2 squared over n2. That. So that's our new standard error. And now to take a z-score. So you'll start with the x bar 1 minus x bar 2, that's your statistic, and subtract the mean of such differences, which is the difference of the means, and divide by the standard deviation, which is the square root of the variance. And the variance of the differences is the sum of the variances. The first variance is sigma 1 squared over n1. And the next is sigma 2 squared over n2. Make a note on this one. Sigma 1 and sigma 2 will be unknown. We'll estimate them using sample standard deviations. So sample standard deviations are S1 and S2. Those vary from sample to sample. So let's just say these increase variability. Population standard deviations don't vary. Yeah, sorry. So Z will become T. Okay, now the hard part with that will be figuring out the degrees of freedom. Because if you think about it, degrees of freedom was always the sample size minus 1, but there's 2 sample sizes with 2 standard deviations. Oh, somebody sees a mistake up above, so let's go back and see if we can fix that. Yeah, so I don't know if you guys see that. I used an n2 twice. Huh, let's fix that. Thanks, Andreas. Okay, any questions? Thanks for that little tip. Absolutely right. Wish I'd have caught it before. Okay, I think we're good here. That's just a setup for the next 2 sections. The first section uses the first statistic we just figured out, and the second one uses this statistic, the z-score, but it'll be a t-score when we finally do it. All right.